Okay. So with that, so graduate projects as a course has a high level objective of introducing students to project management, systems engineering, and what we call engineering project work. That's really hands-on project work with aerospace engineering. So build, test, verify, all the parts of a design cycle that you experience in aerospace engineering. Now, if any of you come from a mechanical aerospace engineering background in your undergraduate degree, you may have had a capstone course that did something similar. However, at least for a capstone course here at the University of Colorado, we always constrain our projects to last one single year. So our undergraduate students get to experience that full design cycle over those 2 semesters. In graduate projects, things are a little bit different. Your graduate students now, we expect the scope of the projects to be quite a bit larger, which means our projects are going to last, in many cases, multiple years. So for our CubeSat teams, for instance, our projects may last 4 years plus. So what this means is that when you join a project, you're not just joining a project that has a certain topic. You're joining a project that is at a certain place in the design cycle. So it might be that you get to experience the details of integration and test, or it may be early on when you're really in that initial development phase when you're doing more design work. So something to keep in mind as you're listening to projects today. It's not just about what you're doing, it's about where they are in the design cycle, which is really going to be what you end up doing day to day as part of the project team. Now for the course itself, again, here at the University of Colorado, there are several ways to meet the requirements of your master's degree. One of them is graduate projects. So if you take 2 semesters of graduate projects, so 50-18 and 60-28, that basically counts as a requirement for your master's degree. The alternatives are to take your certificate or to do a master's thesis. So by completing 2 semesters of this course, you meet that requirement. And again, you'll get that experience we talked about working with the project team. Now, the course is once a week, there's a lecture, which is given by the graduate projects coordinator on general topics. Basically topics of how do you work in a team? What is project management? What is systems engineering? We talk about public speaking skills, and we have quite a few guest lecturers as well. So that's about 1 hour once a week, typically Monday evenings. And then twice a week, you're going to have your lab times within your project sections. Now, there are 2 2-hour lab times, like most lab courses. But what that time entails is really project specific. Pretty much every project has a once a week status meeting. However, the rest of the time is really dictated by the project needs. You may meet with your team, you may meet with sub teams, it may just be work time. And obviously outside of those lab periods, there's going to be additional time to work on the project as well. So at a high level, it shows up in your schedule as a typical lab-based course. In reality, it's a bit more flexible. There's other time that you're going to have to be working on the project. But again, that's dictated by the team itself. Okay, so that's a very high level view of the course. Again, it checks a box for a master's requirement. It also gets you a lot of great experience with project teams. However, really to get an idea of what the course is about, the best thing to do is just to hear about the projects that we have going. So right now we have several projects. The first of which is our human spacecraft design project. It's a project where every semester they're building a new mock-up and they're performing human factors testing on it. We had a new project this semester, an Eclipse project. We also had a new project last semester, ACES, which is developing an attitude determination and control system. And you're going to hear more about all of these from the student teams. We're going to have a new project next fall, which is an aerogel deployer on a suborbital launcher. And then we have a variety of CubeSat projects. So I listed 4 of them here, quite a few going on. And again, you're going to hear about all of them in more detail. So with that, I'm going to hand it off to our first team. This is the order we're going to go for the team's sake. So it's the same order as the mid-semester presentations, except with our new project substituting for contact. So we're going to start off with ACES and then go into the new project. So if I can invite the ACES team up front to go into their presentation. And again, for anybody online, anybody in person, feel free to raise your hand in the middle of a presentation. We can take time. We're also going to have time at the end. So I've asked the students to stick around. So if you just want to walk around, talk to each project one-on-one, there's going to be time for that as well. So, there you go.
Thank you. All right. Hi, everyone. I'm Jessie, and this is Chase, and we are two of the 7 students who make up the ACES graduate projects team. ACES stands for Attitude Control for Precise Sciences. Our PM is Kyle Lee, and our SE is Joe Maselli. Our faculty advisor is Dr. Daniel Kubicek, and we have 2 industry sponsors, the Aerospace Corporation and LASP. Our project is a little bit different than the other CubeSat projects. Instead of designing a full satellite bus, we're designing a single subsystem that could be used on a variety of CubeSats. The subsystem that we're designing is called an ADCS, which stands for Attitude Determination and Control System. Bit of an overview as to what an ADCS does. It's the hardware and the software that control the orientation of a satellite. The types of missions that we're designing our ADCS for are CubeSat missions that are performing astrophysics investigations. And what this means is that it has a science payload that needs to perform a pointing of a sensor, typically a camera, at the sun or a star or a very distant target. And it needs to perform that pointing to a very fine degree on the order of 0.002 degrees, which in the world of satellites is considered very fine pointing, and it makes it an interesting but challenging project to be a part of. The primary hardware that goes into an ADCS are sensors and actuators. Sensors include things like star trackers, sun sensors, horizon sensors, and magnetometers. And the primary purpose of these sensors is to determine the current orientation of the satellite. And then on the other side, we have actuators, which perform an action on the spacecraft that changes the dynamics of it, which allows us to control the current orientation. Common actuators for CubeSats are reaction wheels and magnet torquers. On larger satellites, you might also see thrusters or CMGs, but we primarily stick to these first 2 that I said. And then both of these types of hardware are wrapped up in a whole bunch of software algorithms that together create the whole ADCS. As far as what our team has done since we started in the fall, we've done a whole bunch of software development. We've created our software development plan and completed a few key algorithms, including our BDOT controller and the EKF. We've also done a lot of work on our Monte Carlo simulation that will allow us to test our current system. We've completed our verification and validation plan, which outlines how we plan on testing our system against our requirements at all of our stages in our development. And lastly, and most recently, we've started on hardware selection, so sizing and selecting those different actuators and sensors that I mentioned on the last slide.
All right, so here are some tasks that our team will be working on next fall. So stuff that you guys could be doing if you join this project. So first, we'll be continuing our algorithm development. So that will include writing a variety of simulation and flight software. We'll also be starting to integrate hardware and software into a prototype. And that's going to include the development of a flat set and hardware in the loop testing. And then we'll also be verifying and testing the performance of our system. Here are some open positions that we have on our team. So we're looking for people who are interested in software development. Specifically, you would be writing GNC algorithms and or modeling and simulation software. We're also looking for people who would be interested in doing systems engineering work, and people who would be interested in working directly with hardware and performing tests on that hardware. Here are some skills that would be helpful to have if you're thinking about joining this project. So it would be good to be able to code in Python. It would also be good to know C and C++ as well. It would be beneficial as well to have a good background knowledge about spacecraft attitude dynamics and control. And then having an interest or even some past experience in systems engineering would also be helpful. And finally, since we're going to start working with some hardware, it would be good to have some people with some past experience working hands-on with CubeSats. So that is what next fall will look like for the ACES team. Are there any questions? Thank you, guys.
All right, thanks. All right, well, next up, we have our brand new project. So the advisor for this project is going to be Professor Matsuo, who I'll hand off to in a moment. One thing I forgot to mention at the start, we do have a sign-in sheet, both if you're attending to find a new project, as well as if you're a student who's presenting. So stop by Kyle and he can get you on the sign up sheet.
So thank you, Nick, and good to see you. And then, so we're very excited to share this news of new graduate project, and then we need your help to develop a science payload that goes on a suborbital vehicles. Because specifically we're targeting Blue Origin. So I'm Tomoko Maxwell. I'm a professor in the remote sensing focus area. So here next to me is Valis Valdi. So she's a research assistant in my group. So she has a mechanical engineering background, and then I work on different areas, but I'm primarily in science background. So collaborator, we have a bunch of engineers participating as a collaborators from Johns Hopkins University Applied Physics Lab. So they're pros coming here. I mean, so they are actually working with suborbital vehicles. So here you go. So this is a big picture. So there is a project called Turbo that is a low-cost access to space, low-cost mission concepts studies undergoing, led by Applied Physics Lab, Johns Hopkins University in Maryland. So they have already targeting, demonstrating this capability, new, so cheaper access to space, and then they want our help to sort of develop a miniaturized payload. So basically, I don't know if you heard about chipsats. So we're thinking of chipsats type of sensors. So at this point, we're thinking of more about GPS location recorders, GPS receivers, but they are thinking of putting remote sensing sensors. So there's few things is up in the air, but so chipsats enveloped or encapsulated in aerogel. Right, so that we call it payload. So we call it space drop zone. Okay, so why I want to do it? So there's a space. So the transition region between the Earth's atmosphere to space, where so CubeSats and other satellites LEO orbit. There's a region that's very difficult to access. So it's a sort of last frontier nearest to our ground space. So we really want to take advantage of this ability to tag on the commercial suborbital payload launch. So here you can see that it's called YANAS payload platform that goes between this suborbital basically propulsion module, and then so this top, I don't know if you know, but top part is a cabin that actual humans go. So in between there's this YANAS system, and then so there's a this graduate project will design the payload dispenser system that goes with YANAS. So okay, with that. Okay, so one thing I want to say, so we had a conference call with Applied Physics Lab, and then so next launch opportunity for this, if we really do well, so your payload or dispenser system might actually really go to Blue Origin, right? So there's a possibilities, but there's a timeline that's might be tricky. It may not happen in the spring of next semester, but we definitely want to keep in touch with you. That if you participate, or maybe you stick around for other years, so you could actually see it might get launched to suborbital space. Okay, so Valerie gonna go over a bit more details, what's objectives, but it's a new project. So we are looking for all kinds of people, all kinds of abilities and interest and enthusiasm. So it's really fun to be able to shape scope of the project. Okay.
Yeah, thank you, Tomoko. Like she was saying, it's kind of a very broad overview for our objectives, but essentially we want to design and prototype these space drop sounds, which are like a GPS receiver that's encapsulated in an aerogel sphere, and then also design and prototype the dispenser system that will eject these aerogel spheres from the suborbital vehicle.
The secondary objectives could include exploring location and tracking of the payload and recovering the payload. So actually going out into a field and having a LED light on them, or finding out what the best way is to track and recover these payloads after they've been launched. And then also investigating the aerodynamics and dispersion patterns of these falling aerogel spheres, because this is a new method that hasn't been tested or used before. So some of the tasks that students could potentially do in this project would be material selection and fabrication methods and trade studies for the aerogel sphere housing units, as well as mechanical modeling, testing, and prototyping for the payload dispenser itself, modeling dynamic behavior for the falling spheres, and then of course, cost analysis, risk assessment, and science closure likelihood for the evaluation of this mission concept could be included as well. The set project deliverables we have would be a preliminary design review, a critical design review, and then an operational readiness review at the end. And something that's kind of unique about this project is that it's designed to be 2 semesters, so you could see it start to finish, hopefully. So with that, I'll move on to what the rough project timeline would be. So in the fall of 2022, we'd have our kickoff, and then the phases of research, design, and prototyping for the space drop sounds would take place. Things like system studies, risk analysis, alternatives of analysis of alternatives, and then of course CAD modeling, component testing, and then design review and iteration would all take place in that semester, as well as having the preliminary design review and critical design review. These reviews would also be looked at by our collaborators at APL. And then in spring of 2023 would be the building and integration and testing phase. So that's when you would actually get to build these systems and test them and play around, and then also write that operational readiness review. And as Tomoko was saying, there's a potential for integrating the system with the Janus platform from Johns Hopkins APL, and then also potential delivery to Blue Origin for a launch, which would be really exciting. So yeah, we're looking for a team of 5 to 12 students who are interested in all sorts of things, but prototyping, mechanical modeling and testing, working with additive manufacturing could be a big component of this project. And of course, aerodynamic modeling, simulations, hardware, software components, trade studies, so pretty much everything. And of course, working effectively in a team environment. So yeah, with that, I'll open it up to any questions. If anybody has any, we'd be happy to answer them.
All right, thanks. As you heard, this is a brand new project, and I'll also say you just heard from ACES, which was brand new last fall, and you'll be hearing from the Eclipse project, which was brand new this semester. So it's always a very exciting time to join the first semester. Feel free to talk to those projects as well if you want to hear what that experience is like. So with that, thanks.
Thank you.
So next up is Maxwell. Kyle, is that coming through full screen? Good, all right.
All right. Hi, everyone. My name is Robert. I'm the current project manager for the Maxwell CubeSat team. I'm joined up here by Eric, and soon to be up here is going to be James. So we're going to be talking about Maxwell, which is a satellite that's very close to the end of its life cycle. And then James is going to give a few slides about Ralphie, which is a brand new CubeSat, which is going to be coming right behind Maxwell as well. So we'll kind of go through that during this presentation. So starting out with Maxwell's mission overview, stands for Multiple Access X-band Wave Experiment located in low Earth orbit. It is a little bit of a mouthful. We're a 6U CubeSat, completely designed, built, and tested here, right here at CU. Our principal investigator is Dr. Scott Palo, and our sponsor is UMP through Air Force Research Labs. So we're scheduled for completion sometime in late 2022 with on-orbit operations going throughout 2023. Here are a few of our team leads. So the motivation for Maxwell is high rate comms. I guess we're getting to the point where only a few people really remember what dial-up was like back in our childhoods, but loading images took a really long time. So the motivation is imagining this, high rate data transfer similar to loading an image was critical to national security. That is the motivation behind speeding up this process. So Maxwell is targeting that as well as CDMA, which stands for Code Division Multiple Access. And pretty much what CDMA is a way to superimpose a code onto your signal, which allows it to differentiate itself from others of the same frequency. So the analogy is you have like a crowded intersection, and CDMA kind of turns it into a complex overpass system, allowing each signal to get where it needs to go and be encrypted and decrypted appropriately. So our mission objective is mostly all in advanced RF hardware. So high rate X-band downlink and CDMA downlink as well. We are also flying a chip scale atomic clock experiment, which is characterizing the clock performance against GPS. So this is a cool new area of science looking into GPS alternatives or GPS-like performance in GPS-denied environments. We're also going to be the first CDMA demonstration on a CubeSat, which is really exciting, as well as the first deployment of the T-Dagger antenna, which is a commercial 1U deployable X-band antenna as well. So a couple firsts with this mission, which is super exciting. So our ConOps, the Maxwell will, phase one is ejection and separation, followed by our commissioning, make sure everything's up and running properly. Then we'll do our comms experiment, shortly followed by our CSAC experiment in stage 4. And then we will deploy that T-Dagger antenna I just talked about, and then finally deorbit. We don't have any propulsion, so once we deploy that big antenna towards the end, we kind of pick up some drag and slowly deorbit from about 550 kilometer altitude. So for our hardware overview, kind of what's in the box here, all custom core avionics built and tested right here at CU. 3 radio antenna pairs on board, as well as most of our external ADCS peripherals like reaction wheels, magnetorquers, what we're using for actuation on the spacecraft. So our core avionics I just mentioned, we have an ADCS system, CDH system, which is our command and data handling, and our EPS system, which is our electrical power system. So this core bus is kind of the brain of the satellite, you could think about it. And we pretty much run off of a series of microcontrollers and single board computers. So anyone who has experience, with any of these microcontrollers, definitely come seek us out. We could really use your help. So our current goal is targeting pre-integration review. So it's a series of 4 tests, 3 of which are almost complete. So the 4th test, the one that we need the most help with, is our day in the life test, which is the most comprehensive way of pretty much having your integrated satellite sitting on a lab bench running for days or weeks at a time to try and catch any last remaining bugs. So these 4 tests are full system completion tests and are kind of one of our last checkpoints before flight. So our team organization, what we're looking for in the summer and into the fall. C programming is always an area we could use more people working in. Any electronics experience, SDK or Basilisk ADCS simulation experience. FPGA, if you really want to get hands-on with hardware that is definitely going to be going to space. It's a really cool opportunity, and general interest more than welcome as well. Everyone's learning in some new area, and if we don't have students learning, then we're not doing our jobs effectively. So general interest more than welcome as well, and please feel free to reach out to me or to come see me after this presentation with any questions. With that, I'll pass it off to James, who will be talking about Ralphie.
Thanks so much. So Ralphie is another CubeSat. This is a brand new CubeSat that is just starting in development this past few weeks. It stands for Radio and Path Agnostic Communication Experiment. And this is kind of lumped together with Maxwell since we have the same PI. We're sponsored by the same people, UMP, University Nano Satellite Program. And we have a lot of the same leadership and needs right now. So what you can do is think of, there's going to be another presentation, Swarmix. It's going to be a lot of satellites combined into one. We're taking the core bus and hardware that Swarmix is using. It's going to be about the size of Maxwell. It's going to be a 6U satellite. And we're going to use a comms and a power payload. And that will be our kind of envision right now. And so this is another communications satellite. Right now, a lot of missions are really limited by low rate communications, especially scientific missions. Your rate of data generation really outpaces how fast you can downlink it. So we're hoping to demonstrate optical downlink. We're gonna have a laser transceiver that can go to the ground. And it's gonna be implemented through this path agnostic system. It's basically an FPGA based system that takes in a message as well as a priority level, saying this is really high priority or low priority. And depending on the priority level and the message's length, it will decide what mode of communication it will downlink on. It could maybe do a really robust, available sort of networked satellite communication, or maybe it can do a less available and just wait until the really high throughput optical communication is available. And so this is sort of the novel communication system that we'd be demonstrating. We're also demonstrating a modular power system. This is kind of the first of its kind. It's a SDPC, which is software-defined power system, where we will be using a charge controller integrated into our core systems, as well as experimenting on a power output board. Currently, little slide error. Currently, there's a small amount of people working on it. It's just me and a few other grad students. Brody Wallace, Bailey, and David, which are all on other CubeSats. And we're recruiting for both the summer as well as into grad projects in the fall. In the summer, we're going to be doing a lot of high-level system design. We really don't have any hardware for the satellite yet. We're in these really, really early stages of development. We're going to be developing a CAD model. We're still developing some budgets to make sure that this mission is feasible, as well as doing software development. And so for the fall, we're really going to continue prototyping. We need more software people. We need more electronics prototyping people and power people, as well as structures work to get some more physical hardware. If you have any questions or if you want to sign up, please contact me there, my email, and I'll be around afterwards as well. So if there's any questions for Maxwell or Ralphie.
All right,
Cool.
thanks.
Thank you.
Also, I'm going to be talking more about enrollment at the end. For the most part, each project you're hearing about has a separate section you can enroll in. The exception to that are these CubeSat projects that you're in the middle of hearing about now. The good news about that is we're treating the CubeSats as one project to sign up for. So if any of these sound interesting to you, you can basically sign up, and then going into the fall, we can figure out the exact fit then. So with that, the next one up is Canvas.
Hello, everyone. My name is Brittany Nez. This past year, I've been working with the instrumentation payload for CANVAS. CANVAS stands for the climatology of anthropogenic and natural VLF wave activity in space. A huge mouthful, so CANVAS suffices. We are currently in the very last bit of trying to finish up our project before sending it off into space, and I'll get into some of the things that we're looking to complete next semester. So CANVAS is a 4U CubeSat mission. We're specifically looking at the very low frequency spectrum, where we'll be looking at originators of these VLF waves, including lightning and ground-based Navy transmitters. In order to detect these waves, we are using a 3-axis magnetometer and then a 2-dipole electric field wave detector. For our frequency band, we're looking specifically at a 0.3 to 40 kilohertz range. We're wanting to analyze the electromagnetic energy input in this range. So you can see some of the data visualization that we're hoping to do with this information. I think the bottom image is pretty cool because we're able to see all of the transmission activity that's happening around the world. And the little red dots show where our, I guess, the ground-based transmitters are located, and we can detect that. So I think that's really cool. Last semester, one of our teammates put together a deployment sequence video, so we can see the two electric dipoles and then the deployable solar panels pop out, our UHF antenna, the second set of electric dipoles, and then our boom extends our magnetometer out, so we're away from the satellite. And yeah, it's a really, really neat video. We like to show it off. There's the glory shot of the full satellite. No. In terms of our satellite components, we'll start off on the right-hand side. We have our electric field instrument capping off the satellite with the crown, and then the two dipoles, or I guess four antennas, two dipoles that are going to be traced along the full extent of our satellite. For our ADCS system, we are utilizing a commercial off-the-shelf ADCS from Blue Canyon Technologies. That's the exact box sitting on top of our crown for our electric field. And then we'll move over to our avionics boards. We got our card stack. And then after that, we have our communications, our GPS components. Sitting on top of our boom box it's the giant box there, is our electric power system. And then at the very end, we have our magnetic field payload that will be extended on our boom. In terms of manufacturing, we're pretty much done with manufacturing. There's a few items that we're still waiting for, a few revisions we had to be made, but otherwise everything's here. We're gonna fit check all of our flight revision pieces, and we should be good for assembly. For boards, we have 4 main sections for our electronics boards. We have the instrumentation boards, core avionics, communications boards, and then in the other category is the GSC and battery boards. In terms of electronics, our digital board is flight ready. We're ready to go on that, and we've been conducting testing. All of the other boards are currently in manufacturing. We just got the PCBs, so we're working on populating those, and we're hoping to get into flat sat testing by the end of this semester. For instrumentation, we've been doing a lot of subsystem level testing for that. You can see the list of all of the tests we've completed for the electronics, or the electric field and B field instrumentation. We're hoping to work this from we did work this from the sensor level, then we add on a board for a preamplifier, add on the analog board, so on until we get the full chain signal for our electronics. And it's coming along pretty well. We're getting into flight testing for this. So we've gone through the engineering model level, completed all testing for that. And we will be working on flight model testing at the end of the semester and probably on into the summer. Most of our subsystem and component testing will be completed by the end of the semester. We're hoping to get the flat sat done either by the end of the semester or early on into the summer. And then environmental testing will take place on into the summer, and that will include thermal vacuum chamber testing and vibration testing. This just kind of gives a breakdown of where we're going from the assembly stage of Canvas all the way to when our satellite is ready for flight. So it's a pretty extensive plot, and in its entirety, it's pretty amazing how much we've gotten done. And yeah, we can move on from this slide. In terms of the Canvas timeline, we started off with preliminary design back in 2019. So we've progressed pretty far in this project. In 2022, we're looking at system assembly and integration testing. So we're trying to get ready for pre-environmental testing review. And then we were hoping to launch by the end of the year, but that looks like it's going to get pushed on into 2023. We don't have a launch vehicle yet, so that's what we're waiting on. But in terms of what we would be doing for next semester, it's just tying up loose ends, finishing up any testing that we need to complete before we're ready for launch. I'll take any questions now or after.
Okay, well, we'll have plenty of time at the end as well for questions. So thanks. All right, so our next CubeSat is going to be Swarmix.
All right, hi everybody. My name is David Fitzpatrick. I'm the project manager and systems engineer for the Swarmix CubeSat project. This here is Connor Phillips. He's our thermal lead this semester. So let's talk a little bit about Swarmix here. This is our team. We have 16 people here at CU. As you can see, our PI is also Dr. Palo, same as with Ralphie and Maxwell. So we've got a lot of people here at CU. Dr. Rainville is also one of our advisors on the project. So what is Swarmix? Let's go through the acronym. There will be a quiz, so write this down. It's Space, Weather, Atmospheric, Reconfigurable, Multi-Scale Experiment. That's a quick one right there. So it's one of those crazy acronyms we got going on. It's funded by the NSF, the National Science Foundation, and we're going to have a 3U CubeSat right here, and we're actually going to have 3 of them. So we're going to be launching in a swarm of CubeSats, hence the Swarmix. This is what our CubeSat looks like right here, our CAD rendering. So our 3 main goals for Swarmix, we kind of have 3 different things we're trying to accomplish here. The first one is going to be science-based. So we're going to be looking at the upper atmosphere, taking in situ measurements of the upper ionosphere and the upper thermosphere to analyze the equatorial ionization anomaly and the equatorial thermospheric anomaly. For those of you who have taken atmospheric courses, these are some interesting plasma features and corresponding neutral density features that are in the ionosphere right about 425 kilometers, a little bit lower like that. On the same side, we're going to have an engineering goal of looking at formation flying, which is blocked right here. Formation flying, collision avoidance, and using a hybrid differential drag propulsion control scheme to change the separation between our spacecraft at different phases of the mission. We'll also be doing CDMA downlink based on what Maxwell is doing. And finally, Swarmix is pretty interesting because it's actually a collaboration between 6 different institutions. It's not just here at CU. So we have Stanford involved, Georgia Tech, the Olin College in Massachusetts, Western Michigan University, and the University of Southern Alabama all involved. So this is a really interesting opportunity to talk to people from other schools, get advice from them. For example, Stanford is probably one of the best at formation flying in the university field. So it's very cool to work with them on this kind of stuff. So this is what it kind of looks like from our science goals here. This is a picture of the EIA and the ETA. I won't get too much into this right now, but if you have questions, we can definitely talk about it. We're trying to track how these things change over time. That's basically what we're trying to look at here. These are focused amounts of plasma density and corresponding neutral density at these altitudes. That's the EIA and that's the ETA. And one thing interesting about Swarmix, like I said, is we're moving the spacecraft at different phases of the mission. So during our science experiments, they're going to be pretty far apart, up to 1,300 kilometers separated in spacecraft separation, in the along track separation. And then during OG&C experiments, which we're calling our guidance, navigation, and control experiments, we're going to bring them much closer together, demonstrate some formation and flying, collision avoidance, and things like that. Also using differential drag, which is pretty exciting. And the whole time, we also have a non-zero radial and cross-track separation, again, for safety and collision avoidance. So what this kind of looks like, we've got a cool little video here in SDK to show you. So we model this, basically what happens in the relative frame of what we're calling the chief spacecraft. 2 deputy spacecraft are going to be rotating in almost an elliptical fashion about the spacecraft of the chief right there. So it's pretty cool to see how that goes down. Basically what we're going to do, we're going to take the green ellipse and the red ellipse and the blue ellipse, which are currently on top of each other, and move them further apart. So this is the 0 mean along track separation. So we look at what this picture looks like. There, go back one. This is what it would look like if we separated them out further. So we're going to try and demonstrate this, show that we can do it. We can do it effectively, we can do it safely, and also take some measurements at the same time, which is pretty exciting. So what we're looking for, mostly what we're looking for here is we're looking for people to get involved in our CDH team, the command and data handling team, and our thermal team, which is represented by thermal here. So biggest thing, we need some flight software people. We're in the phase right between our criticals design review and our pre-integration review. So we're taking our design and we're trying to manifest it into actual hardware and taking that software ideas that we've had and actually coding them up in embedded C. So we're looking for flight software engineers, avionics, PCB developers, looking at things like Altium and things like that. Some pretty interesting embedded flight software we have going on, the interfaces with guidance, navigation, and control algorithms. Also looking at trying to get our attitude determination and control system involved. We have some pretty comprehensive and advanced attitude profiles we have to do to maintain a stable power state throughout our orbit. So we have that going on as well. And we're also looking at trying to design our PCBs in-house, getting our designs, taking them from Maxwell, which we've used in the past, and trying to adapting them for our needs here for Swarmix. So if you know anything about C, or Altium or things like that, we're definitely very interested to talk to you. And also with this design, we're looking at taking our design and putting it into a flat set, or our CubeSat flattened out basically. So if you're working on CDH, there's will be a lot of opportunity to actually get hands-on hardware, testing things, communication, make sure things can talk to each other, getting our code to work, and really taking our design, and like I said, making it into a spacecraft. That's the idea. The other thing we're looking at here is a thermal engineer. So Connor's going to be graduating later on this semester. We're looking to try and get some on-orbit thermal analysis to see how our spacecraft heats up with our very power-hungry scientific instruments on board. I'm looking at how that goes down. So again, our CDH, these are all the different things involved. Looking at our EPS, the GNC computer, the Global Star propulsion, ADCS, a couple of transmitters here, and the CDH is basically the brain of the CubeSat that we need everything to talk to. So you'd have the experience to work with all of these different pieces of hardware and make our microcontroller actually talk to them, which is pretty exciting. And looking at the hardware, this is what our card stack looked like. So we had the PCBs slid into the stack right here. You'd be working with all of these, and looking at some kind of block diagrams here. I'm just trying to get all our hardware to talk to each other, which is pretty cool. On the thermal desktop side, this is what we're looking at. So on our thermal modeling, we use this software called Thermal Desktop. Connor's done a great job of that. I'm looking at how everything interacts with each other, designing it, and then doing some orbital simulations that look sort of like this. So we have the Earth going around. We can see how our spacecraft heats up in different attitude profiles. So looking at our attitude profiles, implementing them, and then actually doing a thermal analysis on those to see how we're doing. I don't know why I keep doing that. All right, so that's all I have. If you have any questions, definitely feel free to stick around. I'm going to be around here. Please feel free to reach out to me. We're very interested to talk to you guys. I have a bit of a longer video if you're more curious, like I can send your way. Yeah, that's all I got. Thank you very much. Appreciate your time.
Thank you. So that wraps up our CubeSats. And with that, the next one up, I believe, is our Eclipse team.
Hi, everybody. My name is Kathleen Lawton, and I'm the project manager of the HERD project. We are not a CubeSat project. We are an Eclipse project. HERD stands for HLS, Eclipse Research and Design. Our project advisor is Stuart Tozer. He is in the BioServe department. Our campus customer is Dr. James Navity, and our project sponsor is Northrop Grumman.
So we are tasked with designing by Northrop Grumman, a environmental control and life support system, or Eclipse, for the human landing system, or HLS. The HLS is a space vehicle that will transport crew and logistics between near rectilinear halo orbit and the lunar surface. Upon landing on the surface, it will either serve as a surface habitat or allow access to a pre-placed surface habitat. It will support up to 5 design reference missions. The common requirements for those being support a crew of 2 to 4 for 8 days, support 5 8-hour EVAs, and interface with the Gateway Station and the Orion Crew Module.
Just a little bit about the project scope. Eclipse stands for Environmental Control and Life Support Systems. As you can see in the picture, there are a lot of different subsystems that go into making an Eclipse system, which keeps the crew alive, healthy, happy, and productive. This semester, we decided to focus on a few of these subsystems in order to gain a smaller project scope and go more in depth. So this semester, we focused on atmospheric revitalization, crew safety, and wastewater management. But for the upcoming semesters, we're going to focus mainly on the atmosphere subsystem. Some deliverables that we were having this semester is we have a requirements slowdown. We got a list of over 500 requirements that we were breaking down and making sure we can validate and verify them. We've also done a functional analysis, some trade studies, requirements verification, and some initial flow simulations and CAD models that we are using for our atmospheric revitalization subsystem.
So this has been a pretty interesting project, not just because we're designing a life support system, but because the project was very open-ended to begin with. So this semester, we mainly focused on project definition, requirements definition, and getting a conceptual design of our Eclipse system. And then we mainly focused on the ascent stage of the HLS. Next semester, we hope to further define our system to have a higher fidelity and to further investigate the interfaces of the HLS Eclipse system. We hope to incorporate the descent stage into our design, and then we hope to have more interaction with the Northrop Grumman engineers on our Eclipse system. So just a quick look at some of the things that we've been working out on the left here. That is left, right? Yeah. You can see the pressure control system overview and its interfaces that we've designed so far, and then a CAD model of the HLS ascent stage that we've been using for some TFD simulation for flow and ventilation. And then we have a overview of the internal thermal control system on the left here, and then a 24-hour metabolic crew heat output that we expect our system will need to account for.
So just looking forward to the future, some potential roles that we're going to need for 2022 in the fall is mainly focusing on atmospheric revitalization. So our flow and ventilation team is going to look into ducting layouts, vents and locations, fan sizing, and other components such as that. Our pressure control system is going to look into atmospheric mixing, which will be verified with CFD analysis. Our temperature and humidity control team will be looking into schematic designs and sizing and generating systems that will be capable of supporting the crew, and also getting size, weight, and power estimates. We are also looking for someone who can do command and data handling and flight software. We're looking to integrate some of our software and hardware next semester. So if someone is able to use MATLAB or other stuff like that, we'd be more than happy to have you on our team. We are also looking into making a scale model of the Eclipse system next semester. So we are going to be using 3D printing techniques and also MATLAB to do that. We are also looking next semester for a project manager. So if someone is interested in interacting directly with Northrop Grumman, has organizational and team leadership skills, and also would like to communicate more and work on their networking. Just a little bit more about why you should join HLS, Eclipse, Research and Design. You're going to be interacting every day with Eclipse engineers at Northrop, working on the human landing system and the HALO project. So it's a great opportunity to network with people at Northrop Grumman. You'll also be working with people from BioServe, so its ability to integrate your more into this U Boulder community. We are working on a real project that will inform the design of a real lunar lander. So the software and the hardware that you go into designing will actually be used on astronauts in the Artemis program. We are also able to build some hands-on skills that you can get in some of your classes. So software, simulations, 3D printing, and your communication skills with those people at Northrop. And also you can get some more knowledge about human spaceflight systems. I know some people are in bioastronautics, some people are not. So if you would like to more about how the human is affected in a space environment, you are more than welcome to learn more in the HERD project. We also want to make sure to iterate that there is no definition of what kind of student you can be. So if you are in person, remote, or hybrid, we are willing to accommodate you and make sure that you can get involved in the team if you would like to. So if you have any questions, let us know. We're going to be parked up there, and we would love if you guys would join.
All right, thank you. That was a great comment is made about in-person or remote. That is something that is project dependent. So if you think you might be fully remote or hybrid, reach out to me. I'll put you in touch with the right people in the project to figure out whether or not they can support that. Obviously not a problem with the HERD project. All right, so we have our last project up next. It's going to be the Volt project.
Hello, my name is Denise, and I'm for Volts, which is vehicles optimized for lunar transport. I have Jake here.
Hi, I'm the current financial manager and the structures and mechanisms sub-team lead. Dean is up here with us as well.
Yes, hi, I'm Dean. I was the mock-up lead this semester, and now I just do what they tell me to do.
little background of what we're doing. We're developing a conceptual design of a habitable mobile platform for the lunar surface. It's echoing.
No, that was me, sorry.
Are we good now? Awesome. This vehicle is meant to keep 2 crew members alive for a 14-day sortie on the lunar surface for day and night. And further this semester, we have completed a mock-up of a low fidelity cockpit, and we are currently performing human factors testing of that mock-up. We are also working on a feasibility study of a ZAP truck for future mock-up and other trade studies to look at how to mock up this vehicle and future semesters. Another deliverable that we are presenting is a Blender model of the cockpit mock-up to the Trinity team, which we'll talk about here in a second. That will give us a VR look of the cockpit. Talk about kind of our leadership and mentorship team here. Colonel James Voss is our main point of contact. He is a previous astronaut and is working as our senior engineer. Rick Heeb serves as our senior management. Whenever he's able to come and help, he gives us a lot of great advice towards our mock-up and design. Dr. Mary Sanchez helps us with different human factors testing throughout the project, tells us what we're doing wrong and right as far as testing humans. Dr. Ali Anderson is the lead for the Trinity team, as I mentioned, and they are working on seeing if VR training is as effective as in-person training. So that's what they're using our mock-up for comparatively with VR. Here's a general design concept of what we've created so far this semester. Now we started this project this semester, so we went through a functional decomposition, requirements review, design review. This is our deliverable at the end of the design review. You can see the many different subcomponents that our team is broken up into, such as controls and displays, avionics, crew accommodations, and those are all kind of color-coded throughout the left there. And now I'll hand it off to Denise.
Thanks, Jake. So we're a pretty big team. We're about 14 people currently, and last semester we were 12 people. So we go through a pretty big cycle of designing the product, building the mock-up, which is usually pretty larger scale. And then we also perform human factors testing. That's sort of the general life cycle for each semester, but some semesters might be more design heavy, like this semester, as opposed to more build heavy as last semester. So these are some of the design, which combines some of last semesters of the habitat, deep space habitat, as well as the rover on the top, some suit ports that were designed, and that's our cockpit from our CAD model. And we also performed some structural analysis from last semester on our mock-up itself, like the deck, to make sure that our habitat could withstand the loads on the deck. And then we go into the build phase, which is basically our mock-ups. They range from lower fidelity, like the semesters, to higher fidelity and medium fidelity, like last semesters, which included some galley and sleep stations and exercise station, as well as building the deck. And then we go into human factors testing, which the goal is to evaluate the design through the mock-up. And that requires a lot of different things like completing our human factors documentation, which is pretty in-depth, as in like test procedures, our pre-test forms, our questionnaire afterwards to evaluate the design, and also doing test monitor evaluation forms and a safety plan. So if you really like working in more of human factors and thinking about ergonomics of design, then this is a pretty good project to experience that. So with that, we'll probably take questions at the very end, or you can contact us through Dr. Randall. Thank you.
Yep, and once again, we'll stick around for a little while after the presentations wrap up if there are any questions. And since that's our last presentation, that's almost where we're at. Before we go on though, I wanted to mention a couple things about how you actually enroll in graduate projects. If you've already tried to enroll, you would have noticed you can't. There is a hold on this course. The reason we do that is some of our project teams have different requirements. Some of them have wait lists to make sure that we don't get too many people signing up. Other ones want to make sure that there's a good fit with skills, especially if it's a project that's just about to end. We want to make sure that you don't join the project expecting to be able to do design work when really they're at the stage of build and test. So that said, if you want to sign up, really email me. I'll get you set up for that. I'll put you in contact with the right people or just forward it to the graduate advisor who can lift that hold and enroll you in the course. So again, if you have any questions about enrollment or any other questions, feel free to reach out to me. Also, this presentation is going to be available on the website. So all the emails that people have linked in terms of the project teams, that contact info is going to be available as well. So with that, I'm going to wrap up. Again, everybody here in person, feel free to wander around, ask questions. For everybody online, what I'm going to do is I'll stop sharing, we'll stop recording the Zoom, put questions in the chat, and we can have people from the team just come up to the laptop and answer questions live that way. So with that, I'm going to stop talking. And again, Kyle, you can stop recording. And we're going to go just into the